So the second talk. You see there's that joint paper with Wolfgang. So there are people in this room who know this paper well. This has just appeared last year in the Annals of Statistics. And it's about common functional component modeling. So it's, as I said, this theme is always with this functional principle component analysis. And well, start again with this thing with this Cohen-Laev decomposition. So what you recognize now, I here have changed notation. It's now a completely different notation. I hope you have to adapt to it, because what was previously t now is n. So the number of curves is n. Yeah, that's a more usual thing. And there will also t appear, but the t is now the number of observations per curve. So it's just the opposite of what it has been in the previous talk. Sorry, but that's life. We have different papers in this, and do not present a book. Okay? Okay, please keep that in mind. So the x's now, the xi's now are functional observations. Okay? The x's are functions, no longer f. N is the number of curves, and later on capital T will be the number of observations per curve. So just inverse of that. Okay? And mu is the mean function, and these are something now the Cohen-Laev decomposition. Fortunately the gamma is still the same. That's the eigenfunction of the covariance operator. So J, gamma and J is the change function principal component, and the betas is what were the thetas before. These are the factor loadings, right? So just these integrals. And the variability of the beta is lambda. If you have Gaussian process, a Wiener process, then the beta ij is independent of beta ik for j different of k. And so this is the basic model for functional data, and many people now just do functional data analysis on assuming that the xi, these curves, are observed. Well, okay, usually perhaps a discrete grid, 1,000 points, but that you really observe the curves without error and anything. Okay, so that's what available functional data, which is sometimes the case. There are cases where say functions are recorded even on an analogous scale. That happens. So over longer time periods, for example, and where you say, well, these are the functions you are given, no observation error, nothing. And the point is now with this Cohen-Laev decomposition, one aspect is always this best basis, which I already told you. So if you just don't go to infinity but to infinity L, it gives you the best, sparsest possible basis to describe your functions. Yeah? It will usually be much sparser, much better than Fourier basis or spline basis or whatever you assume. But it also means just to characterize the covariance structure of your process, because if you have functions, well, you have no longer the covariance matrix. So in a way to characterize this structure, well, okay, the way is to characterize the gammas and the lambdas. So a lot about this covariance structure of a process is just given in terms of this Cohen-Laev composition. Which are the principal components? Which are the gammas? How do the lambdas, for example, decrease with R? So you have the first principal component with the biggest lambda, the biggest variance, the second biggest, and so on. So essentially, in a way, in order to characterize the distribution of an x of a functional value, this is one of the basic tools to do that. So it's much more important than any principal component analysis and multivariate analysis, because it's a big theoretical tool just to characterize distributions. Because if you know the gammas and the lambdas, you know about the covariance structure of your process. And there's not much else you can do about this covariance structure. And okay, so that's a basic thing, just to represent functional data and to access the properties. Okay, so this is again what I already talked about, this best empirical basis. If you just go to L, there's no better way to approximate a function than by using principal components. So it's the sparsest possible basis. And it's also a linear transformation with maximal variance. Okay, so now what we consider here is a little bit two sample problems, that we have not one sample of curves, but two. And we want to compare the distributions of these curve samples. So we have sample 1, say, consisting of n1 curves, sample 2 consisting of n2 curves. At the moment here, just assume we have the curves, okay? You know them. And so the problem is now, for example, how does this structure, this sample differ from this one? Or the underlying random variable, the underlying distribution from this one differ from the underlying distribution of that one. Of course, first hypothesis would be they are identical. But if they are not identical, then it can differ in many different ways. These are functions. Functions can be different in many, many different ways. And one thing, of course, to access, say, similarities and differences between these distributions is to consider the different Kahuna-Leibniz decompositions for the two samples. So that you have for P is 1, 2, xi of P, we have the Kahuna-Leibniz for the first and for the second, and now you consider are these different elements, components of this decomposition, how far are they identical, how far are they different? If they're all identical, distributions would be the same. And if they are different, well, what can be different? Means can be different, that's obvious, right? Mean function. But the mean function could be identical, but for example, first principal component could be different. Or even mean function principal component could be identical, but for example, the eigenvalues of the covariance operators, it means the variance of the betas could be different, right? And of course, this gives you some information. For example, it may also be interesting to see is the functional structure, the basic functional structure, basically identical, which would correspond to the hypothesis. The mean is principally identical. The gammas, which depends, the gammas are functions, yeah, to determine the functional structure, are identical. Only perhaps the betas, these coefficients, perhaps their distribution is a little bit different. So if the functional structure is the same, but for example variances are different, so one is more variable than the others. For example, one sample, the variance of the beta, lambdas, may be bigger than for the others. So there are many different ways where they may differ. And that's essentially a little bit the topic of this paper, that we want to do, say, tests for the different components to see whether they are different or identical. So, for example, what we consider here is something like, we consider the different components of this Kahuna-Leibniz decomposition in order to see whether they are the same for the two or they are different from the two. So, for example, the first one is, of course, means. Are they identical? Have they the same means? Do they have, for example, the same eigenfunctions, the same principal components? Gamma R1 is equal to gamma R2? Or are they different? Or, say, the point is, of course, they could be, say, gamma 1 and gamma 2 could be different. Nevertheless, the space spanned by gamma 1 and gamma 2 could be the same. This is possible. Yeah? So, for example, they could just be interchanged. For example, one eigenfunction is some sinus function, the other is a cosinus function, orthogonal, but for the first sample the sinus is more important than the cosinus, for the second sample the cosinus is more important than the sinus. So in this case, for example, for the first sample, the sinus would be the first principal component and the cosinus the second, but just the other way around for the second sample. So this could be. Nevertheless, the space spent by the first two eigenfunctions, but the first two principal components would be the same. So they would describe the same space. So this is also an interesting hypothesis that may be different, but nevertheless they generate the same space. So you can approximate them by the same basis functions. Which will also say in a way this functional structure is identical, only they are realized in different manner. And of course also these lambdas, the eigenvalues, these correspond, as I said, recall to the variance of the betas of these coefficients. So they may be, in a functional sense, they may be quite identical structure, but for example, different variability, which will be expressed by means of the eigenvalues. So you have a lot of hypotheses you could access here. And so each gives different information about, say, equality and differences between the different samples. The application, well, I don't want to say too much about that because most of you know this application better than I do, because it's to implied volatility modeling. And so there was an application in finance, and what we essentially look a little bit here in this thing, we have implied volatility functions for different maturities. So these are the surfaces, and what we essentially would be the two samples, essentially what we consider are something like the log returns of the alpha surface for 1 month maturity and 3 month maturity. So these are essentially two different samples we consider here. But we want to say, are these distributions, how far are they identical, how far are they different? Obviously they are not identical. For example, what you see here is much higher variance than there. So there's much more variation. But of course this doesn't say that the functional structure, the basic functional structure isn't quite close. Maybe close, it would say that in the betas. So different eigenvalues, lambdas, so that the betas are more variable. In this case and in this case. Yeah? What you of course see is that the lambdas can't be identical. But for example, the gammas and the spaces of these functions could be identical, so they could be modeled in the same way. And in fact, they seem to be quite close. For example, what you see here are the estimates of the first 3 principal components, gamma 1, gamma 2, gamma 3, major sources of variation. That's the first one, second one, third one, and you see for the 1 month group, the 3 month group, and they look really close, don't they? So we may have the hypothesis, well, this functional structure is quite the same. But you also see these principal components are, of course, here much simpler than the one you saw in the case of these densities, which are much more complex. These are quite simple functions. Okay? So that's the basic idea. We want to compare, for example, now see these two seem to be fairly close. Is they not identical? Now, to see, is this difference significant? Or can you say that's the same thing? Or is at least the space spanned by the first 3 principal components, is this the same? So, okay, so what can be done? Of course, this is something like an inference problem. In this case, we want to test different hypotheses concerning these principal components, eigenvalues, and so on. And of course you have to estimate these things from data. And if now you knew the curves xi, true curves, then of course you could in principle construct the empirical covariance operator. It was a gamma before, now it's a c. Okay. Of course here this thing is always the same, this integral, the inner product, the integral of x minus x bar times c. And there, of course, there are already some literature about it. How good are these estimates? How do they differ from, for example, eigenvalues, eigenfunctions of this thing? How do they differ from the true eigenvalues and eigenfunctions of the true covariance operator? Depends, of course, on the sample size. For example, some people have shown that's of the order n to the minus 1/2, parametric relative convergence. Okay. And for example, what you have to keep in mind for the rest of the talk, we have gamma r and lambda r. These are truth. This is truth. Then you have gamma hat and lambda hat. These are for the empirical for known curves. And what we, just to determine that, what we can consider is this dual approach, I already used in the density context, that instead of the covariance operator, you consider this matrix of functionals. This is now n times n matrix because we have n curves, right? Before it was t plus t but now n takes the role of the previous t. And this would be the empirical covariance operator. And we have some eigenvalues and the eigenvectors, and well, in the same way you can show that the eigenvalues of the empirical covariance operator lambda hat are just this L divided by N. And essentially you have again these properties that gamma hat, that's the eigenfunction of the empirical covariance operator is just some weighted average of your xi functions. And the weighting is done by the eigenvectors of the M matrix. That's just as before. Okay? That's just as in the first paper, just with a different notation, of course. I'm sorry. Okay, but the problem in this context is, of course, these implied volatilities, for example, I showed you, there's nothing that is just given by nature. That's something you construct from data, right? So they are estimates themselves. Okay? So what we assume here is, well, it's a simplified model that we say essentially we don't observe the x's directly, but we only observe them with errors. We observe them at discrete time points, which we call TIK. This depends on the middle curves. You may have different observation points from curve to curve. And you always have an error term, the epsilon ik. So that's something that adds an additional problem because you have something like an errors and variables problem. The variables you want to consider the x's, you don't observe them directly, only some discretized version with error. And of course you have to take care of that too. And of course the epsilon are usual noise terms. And we have now the t plays the role, there's a number of observations per curve. Okay? Number of discrete observations per curve. And okay, so what we do now is just we want to estimate the elements of this M matrix by using our data. That's just as we did with densities, because in densities we had the same problem in the way. In densities we had this theoretical M matrix with the true F's, but we don't know true densities, so we had to construct our estimates, and here we have to test the same thing, except that now we have a regression problem. But essentially what we do is something like a very similar procedure, which says that what we do here is to estimate the elements of M is just, well, we do interpolation and integration. Essentially we don't even use a kernel estimator here. If we have just your observation, say if you have here your observations, here is your TIK, and here are your Y's. Okay, these are your discrete observations. We just interpolate this thing as step functions. This gives you non-continuous curve, but nevertheless something you can interpret. Yeah? So the functional approximation are just step functions of the values of y, and just this definition. Okay, we just first estimate. Yeah, of the x's are these chi's, which are just interpolations of your y data. We don't care so much about variance because later on for the M hat we have to integrate that. And these integrations, like summing, it will just kill a lot of this noise. Right? You can't do that for densities, but for a regression case that's okay. And so we estimate the M hats just by integrating, which we subtract the mean and integrating over these chi functions. Where again, okay, small thing, you have a possible diagonal bias due to the fact that the expectation of xi of this chi I square is sigma square. And to avoid that a little bit, if you have a diagonal, so the diagonal elements of M, MII, if you have the same curves integrated with itself, we just shift this thing. So for the second curve, we just forget about that and shift this thing here, this thing here, this thing here. Which means that always say for example, yi, this one is multiplied with this one is multiplied with this one. And because you only shift by one time point, one observation point, this won't produce a big bias, but this will avoid that you have something which is close to the variance of epsilon, sigma square. So that's again a removal of diagonal terms, and this is our estimate. So you see, it's essentially based on a regression version of the ideas which are used in density context. Okay? And so you estimate this m, and then from this m, using the formula as I showed you before, that you estimate, you give an estimate. This is the gamma, this is the true gamma hat of the empirical covariance operator, if you knew the true curves, which is the weighted average of your x functions using the PIRs. But now, of course, we have, this would be the true m. And the problem is we don't know the true m, we estimate it. So we use this from the estimating m hat, which we constructed using this type of rules, and get an estimate using the same formulas, which are with the estimated p's, estimated lambdas, gives a gamma hat RT. And so the point is a little bit, what you have to take care here is I also have a gamma hat RT, and the lambda hat RT, and this is just the estimated for discrete data. And this insists of that because, so you have something like, you have two types of errors. You have, one is the difference between the empirical versions, empirical eigenfunctions, empirical eigenvalues, and the true one, which are just the population analogs. And of course, because you don't know the curves, but you have to estimate it from discrete data, you have another error. So you don't even know this one, you can only estimate, can only determine gamma hat RT. Depends on your observations you have. So you have an error from here to here, but you also have an error from here to here. Yeah, so we have two types of error. This corresponds to the errors in variables problem. And also, if you want to do inference, you have to account for these two errors, this difference as well as this difference. So, okay, just some note about here what we use to estimate I have here the x hats. These are the x hats in this formula are just some, say, kernel or spline approximations of your original curves given the data, and the xi hat is, for example, local smoothness with bandwidth v. If you have, or if you use local polynomial regressions, the bandwidth b. If you use smoothing splines, the smoothing parameter b. Something what you want to do. Okay. Okay, then choosing the best parameter would be done by cross-validation in this case, where we choose it in such a way that you get the best approximation by the resulting estimates of the gamma hats. Because you know the true ones should give the best basis approximation. So it's not quite the usual cross-validation. Okay, just to get you some asymptotic results, because this is something, the basis of our two sample problems. If you have a one IID sample, which is almost showing twice continuous differential function L2, and x hat determined by local linear or not our Watson estimator with bandwidth v, then you get something that this is the first result that gives you the difference between these two, this thing and this thing, these two. How far is gamma hat RT from gamma hat R? And you see that depends, of course, on the bandwidth you use. This depends on the number of curves you have, and T is the number of observations per curve. But what you see also a little bit is, it's not too bad, because it's always NTB. This is a variance term, and it depends, of course, so the quality will go up if you have more curves, and if you have more observations per curve. But it doesn't only depend on the number of observations per curve, but also on the number of curves themselves. So you get the gamma, get better estimates of the gamma than you get of individual curves. Because if you have an individual curve, you have only the observations for this curve. Whereas for the gamma, you use information from all curves. So you get better estimates. Okay? And essentially, you can show under certain conditions, if t is not too small compared to n, and if good bandwidths are is used, then the difference between these two is smaller, essentially, than the difference between these two. But I will show you more details in a minute. So this, the second result, and that's the most important because it's the basis of the test, is what's the difference between gamma hat and gamma. So between these two things. The first result, between here the empirical one and the truth. And the empirical lambda hat and a true lambda. And you see here, that's an asymptotic result. It's something like the sum S not equal to R. That's the difference between the gamma times this expression plus a remainder term which is of order n to the minus 1. What you see is essentially the rate of convergence is n to the minus 100. Okay? So, and so essentially, so what you get here, that's an asymptotic result. Essentially, asymptotically, this will converge to a normal distribution with this variance. Well, it's important what you see here, this difference lambda s minus lambda r will get problems if there are two eigenvalues which are identical, then it's over. So what you have to assume, and that's always assumed in this context, that all eigenvalues are different. Not too far together, not too close together.
But you assume the continuous differentiable, and you estimate it as it is continuous.
Yeah, but that's only for this integral, for estimating the integral, you know? For the m is an integral over the function. And I can of course integrate over that. And that, it's not important that this is a good estimate of the x. It's only important that the integral of that is a good estimate of the integral of x. And that's fine. Because by integrations like summing, and all the variants will just the mean cancel out.
But then would that be equivalent if you just use a discretized covariance matrix?
Probably you could have similar results if you use a discretized covariance matrix. Essentially, in the third talk we do that, and but I think nevertheless there are some practical advantages of that. You get some rates of convergence, for example, for the eigenvalues which are of the order n to the minus, which are really of parametric order of convergence, which you could not achieve with that because there's always a bias problem in that. But I don't know whether it's a big difference. I think it's more logical because, okay. So these are these results. This is our importance insofar because it gives the basis. Later on, we will derive tests for the equality of the eigenfunctions. And so this is the first result for the convergence of the eigenvalues. So you get something like that. So it's also asymptotically normal. So I have some, well, this is the variance here. And so this is something like convergence of the mean function. X bar estimates mu, the true mean function. That's the average of the curves. Okay, so these are some asymptotic results about distributions of for the convergence of eigenfunctions, or the principal components, and of means and eigenvalues. What is of course a problem in order to use that, because for this I only have some rates of convergence and so on. It's much more difficult to get real distributions there. And when is the estimation error? That means the error, difference between this and that. When is this negligible? So that you can really say, okay, it's like I can treat the things as if I had observed the two curves. So if I'm already in this world. When is this the case? Now, if you, from the results we have, if you compare the rates of convergence, of course there's, for example, the case if t is larger than n, and you use an optimal bandwidth b for this approximation of an individual function of t to the minus 1/5, then it's okay. Then these are smaller order of magnitude. And you can essentially asymptotically neglect it. But this also works if t is smaller than n, but for example, at least that t is larger than the square root of n. At least you need that. And use an undersmoothing bandwidth, which is of the order b and to the nt to the minus 1/5. So in these two cases, the estimation error is negligible. That means at least that t, the number of observations per curve, must be at least as large as the square root of n, which is not too strong, I think, in many cases. And you have to use a reasonable bandwidth in this case. And then in these cases, you have, this is a small op, so the differences between these two things here is negligible compared to this difference. And you can use the asymptotic results. So the asymptotic distributions then also hold for the estimated ones. Okay? I must say there's also theory developed now for cases where you have really, the number of observations of course is really small. Say only 5 or 6 observations per curve. And which is called sparse functional data. This is a type of a sparseness theory. And they additionally assume that this is a random design. And what they then try to do is to reconstruct from this just a covariance function as a two-dimensional function by non-parametric estimates, and from this one to get then estimates of the lambdas, the lambda head and the gamma head. So these are some papers by, for example, James and Hasty and Hall and Müller, who have tried with very few observations. But that's not our thing. So here the t must be not too small. Okay, here you see some simulation results a little bit about. You have a two-component problem. Exists as two-component sinus and the cosinus. These are the two principal components with different betas, the scores, which have some distributions. For example, what you see here is a little bit. These are simulated curves, some approximations where added some noise, so it looks quite wild. And then these are something like estimates of the eigenfunctions, the first eigenfunction, which is the sinus function. This is a true one, and these are just some different estimates. Okay. But now, we were mainly interested in two sample problems. This was just a theory for one sample. For one sample, how far is gamma r from gamma head, how far is lambda r from lambda head r, and when can you neglect this additional. And now, if you want in a two sample problem, you want to see how are the different components, are they identical or not? Okay, so you have two samples now, the x1 and x2, just from the beginning, and you compare the coordinate left, the compositions. We want to test whether the mean and the gammas are the same.
Could you explain why it was interesting to look at this problem? If you recall this implied volatility surface example?
I don't want to speak about the implied volatility surface example because you know that better than I do. So you can discuss that under yourself because, I mean...
We have a new read of PhD students here who don't know Michael Benko. Would it be interesting if I can tell them?
Yeah, just tell them because this is something, well, you know so much better than I do that I don't think it's so reasonable. Okay? Okay, so what we do is just the distribution, compare these distributions, and now to develop tests for this. And for example, the first hypothesis may be, for example, the arc principal component for the first sample is equal to the arc principal component of the second sample. Are these identical or not? And for example, for the implied volatility example, we saw that graphically they are quite close, at least for the first three, R's 1, 2, 3. That was the only thing we considered. And so how to test that? Well, the point is test statistics, very simple, just use the difference here between the estimates. So gamma hat 1 minus gamma hat 2. And the only problem in a way is, okay, this seems to be reasonable to consider this difference, but what's a critical value for that? Just to get critical values for this test. Well, the first thing is, of course, under this hypothesis, here, you could, of course, this D is identical to this test statistics. Sorry, there shouldn't be an N here. where you just here subtract for gamma hat minus the true gamma 2 minus the true gamma. Because the two are identical, so this cancels out. Right? But this only cancels out if the null hypothesis is true. If the null hypothesis is not true, there's a difference between this delta and this d. In this case, there is a shift, and the delta will be the d will be much larger than the delta. Okay, and so essentially we calculate critical values for this thing. And the power of the test is just if the null hypothesis is not true, well, this distribution will not be close to that one. This will always be much larger. Okay? Of course, now that's not easy to calculate critical values because you don't know the true gammas. You cannot even calculate delta t. You cannot even calculate the value. You can calculate this value, but not this one because you don't know the true gammas. But what you can do, what we do, is just bootstrap. And all the asymptotic results before were just very important to derive then bootstrap works. Bootstrap is consistent. Because in order to do that, you need to know asymptotic distributions, otherwise it doesn't go. And so the bootstrap approximation, and so that's the idea of the test, the bootstrap procedure. The distribution of this delta, I showed you, depends on the unknown true eigenfunction, but can be approximated by a bootstrap distribution of delta star. When you consider delta star, that's gamma hat star minus gamma hat 2 star minus gamma hat 2, and gamma hat 1 star, gamma hat 2 star estimates to be obtained from independent bootstrap resamples of your original sample. But essentially you only don't only resample curves, but because you have discrete observations, so essentially you resample all the observations you have. And of course, I mean, this is the bootstrap analog of these statistics here, which you can't even calculate directly. Okay? So this replaces the true eigenvalue, the true principal component. This replaces the estimate. And what you do now for this bootstrap test, you draw a lot of samples and then determine the critical values for this delta star. And this gives you then critical value for the test. Okay? The point is that under H0 we have that the d is equal to the delta as a totally correct level, the bootstrap works, and under H1 the two are not identical, and so the distribution of d has nothing to do with delta, and this gives power of the test.
But under the Null hypothesis, did you estimate the gamma from the whole pool sample? Estimate the gamma from the pool sample, gamma 1 and the sample 1 and sample 2 together, and then you estimate the common eigenfunction?
No, that we don't do. We don't do. That we do separately. Okay? The one is you could do that, would be not a procedure. Okay, that would be not a procedure. But here we resample the gamma hat 1 is obtained from a bootstrap replicate of gamma 1 of the first sample, and this is from a bootstrap replicate of the second sample. So that's different, right? It's not everything mixed together. Well, okay, it's not such a big difference. Okay.
So I suspect the difference will be larger if you estimate the common function from the two pooled samples. That will be, it will not be close to neither to gamma 1 or gamma 1 hat nor to gamma 2 hat if they are not the same.
Well, I mean, the problem is, of course, you must be careful. For your underlying sample, yeah, the null hypothesis may be true or not. You don't know. Nevertheless, you have to determine the null distribution from your underlying sample. That means you must use something which works independent of whether the null hypothesis is true or not. Otherwise, you can't calculate critical values. And here the point is that, of course, essentially, what we make is the distribution of this thing. For this thing, it isn't really, for the distribution of that, it's not so important. Say, for the distribution of that, it's not so important if this is equal to that. What's important there is the difference here, the difference there. But it's not really important whether these two are identical for this distribution, because these are also independent samples. So in a way, this gives you the correct distribution for delta in both cases, if the null distribution is true or not. It doesn't matter. It doesn't really matter. It's only if the null distribution, if the IH0 is false, then this distribution doesn't correspond to that. And that gives the power of the test. You see? And you must be careful, because, I mean, otherwise you must always, if you must do correct resampling. And for example, if you just resample your data, you don't know whether the null hypothesis is true or not. All right? And you can't, and you don't mimic anything if it's really based on the hypothesis it's the null distribution is true, but it's not. Then you're bad. Then you're lost. But in this case, it doesn't matter whether it's true or not, the distribution of this delta, because this doesn't depend whether this is equal to that. This depends only on this difference. And the asymptotic distribution for this difference, because the two samples are independent, so it doesn't really come in. And you could not really use a procedure where whether or not this gives the correct level depends whether or not your hypothesis is fulfilled for yourself. That's exactly what you want to test. Okay. And in a similar way, you can also make a common eigenspace test, where you consider something like so the kernel functions which define your projection operator into the eigenspace. So essentially consider this whether this is true or not. So the eigenspace, that means that the first L principal components approximate are the same linear space. And so the test statistics is just this difference here. And well, you mimic this by the asymptotic distribution, where you use a subtractor true one in the bootstrap analogs. That's exactly the same idea. And essentially also the same idea when you want to consider differences between means, consider differences between the eigenvalues. You always consider this type of test statistics, and critical values then are approximated by using these differences here. Okay? This is exactly the same idea for the gammas. And theoretical results, just based on this asymptotic distribution you get for the case of one sample, are just in a way these things that the bootstrap works, is consistent. Because this says that the distribution of these delta statistics, yeah, so the probability that delta is larger or equal to some fixed value, minus the conditional distribution of your delta star given your sample, and this difference, the conditional converges to zero. So the bootstrap is consistent. Okay, and this is how it's for all different statistics, for the statistics you use for testing same eigenvalues, statistics you use for testing are this the same eigenspaces, same means, same lambdas. Okay, these are the theoretical results. Just some, also gives you some simulation examples in this way. You have, for example, here again, this thing where you have just a family of functions which only consists of two components. It's a very simple one, two sinus components, called VR1, VR2, with different betas. And the second one, either it's the same or it's something, these functions t plus a shift delta. So in this case, this is not equal to that, this is not equal to that. Okay, it's just how big this shift is, says how big are the differences between here, this one and this one. Okay, and for example here for the bootstrap test you see a little bit for n equal to 70, t equal to 100, so there's no shift. The critical level in principle it's test level 10%. This is something like now different situations, different distributions of the betas, and so it's if the null hypothesis is true, the level is approximately 10%, and this is a little bit about the power. That here the null hypothesis is not true; they are different, and well, you see if it's sufficiently different, the power is essentially very large, equal to 1. Okay, and further, last thing about implied volatility modeling. And here you see again these log returns here, and for example here these different eigenfunctions in this case, which look quite similar. And for example, you see results of our test. This is just the variance explained. First component explains a lot, 90%. And for the first component, the test rejects equality. Whereas, for example, for the eigenspace, that the first 3 components are equal, that's not rejected. That the first 3 components altogether span the same space, that's not rejected.
In this case, may I ask, you have actually several hypotheses which you test at the same time.
Yeah.
Do you correct for multiple tests?
We did not Bonferroni, no. No.
So it's not.
At least I think I didn't do it.
Not Bonferroni, just you do critical value for every particular test independently.
Right, yes, yes. So we did not really consider multiple testing problem there. Absolutely not. I mean, you could do it, of course.
Just to know what.
No, this was just every hypothesis separately. Every hypothesis separately. Okay, that's already this talk.